In this lesson, we're going to tackle some uglier integrals. So you can see an example of what I'm talking about here. We have the integral of 5x times the fourth root of 6x squared plus 5 over 4, all with respect to x. So this is quite a bit uglier than the integrals we've seen previously, right? And if we try to look this up on our derivatives rule sheet, we wouldn't find it, right? There's no function whose derivative is just this that we know of. So we're going to use a method, and you guys are going to find this pretty satisfying because it's really clever. We're going to use a method called substitution. It's often called u substitution because u is a variable that we use just kind of by convention. So substitution or u substitution is the method. And to use this, the first thing we're going to do is we're going to recognize that we have a function inside this root, and we have essentially like a multiple of the derivative of the function outside, right? So if I take the derivative of 6x squared, I get some form of just like the linear x function, right? So that's what we're looking for to use this. And what we're going to do is we're going to be really smart, and we're just going to change variables here. So I'm going to say I'm going to let u, here's my u substitution, right? Let u equal 6x squared plus 5. So I've taken this inside function, and it's often an inside function that we let u be. Then I'm going to say if this is u, well, the derivative of the u, du, is 12x dx. So 12x dx, this lets me know that I took a derivative with respect to x. And then this statement gives me the relationship between this dx operator and this du operator. Okay? So what I want to do is I want to get just x dx by itself, because notice, here I'll highlight, we have x dx in our original integral, so I want to write du in terms of that x dx. So I'm going to say 1/12 du equals x dx. I divided by 12 on both sides. And now I can substitute. So the first thing I'm going to do is I'm just going to rewrite this. You don't have to do this, but this I think will make it clearer to see. I'm going to factor out that 5/4. And then I have x, and then fourth root of u dx. So I made my first substitution by just plugging in u. Then, again, x dx is 1/12 du. So I'm going to say 5/4. And then times 1/12. I'm going to write the du over here because that's the convention we write at the end. And then fourth root of u. And suddenly this has just become a power rule integral, right? So that's pretty cool. We've massively simplified this. Now, we'll just do the work here. 5/48, right? So I multiply my fractions together. So I'm just simplifying, and I can rewrite this as a root to the 1/4. And then I integrate, so I add 1 to my power, and then multiply times its reciprocal, right? So 5/48 times 4/5. Because I know when I do power rule, these will cancel out, and that will get me my u that I want. And then I can say 20 over 240 u to the 5/4. And don't forget your plus c. And then I'll just simplify that sum, so that's 1/12 u to the 5/4 plus c. Now, we're almost done, but we want to put this in the same variable that we started with, right? So instead of saying u, I'm going to replace that with 6x squared plus 5. So here's my final answer. So that's my indefinite integral. This would be a great time to pause and just make sure you followed all that. Particularly, you want to think about my u and my du, so make sure you understand how I got that, because that is new. And then you want to think about this substitution, so going from x dx to 1/12 du. That's a really important step that is challenging as well. The rest of it is the same once you've changed variables as the integrals we've been doing before, but those are the steps you really want to zero in on. When you're ready, we're going to tackle two more. Okay, so here, this example, notice x to the third and x squared. So my u is going to be the bigger power in these power rule ones, because I want the derivative of u to be sort of outside my substitution. So I'm going to let u, you can use any variable you want, you don't have to use u, by the way. You can use w for Mr. Right. Probably don't use x though. Let u equal 6 minus 5x to the third, and then du, well, du is going to be negative 15x squared dx. Okay, so those are my substitutions. And then I'm going to make x squared dx. I'm going to isolate that. So negative 1/15 du is equal to x squared dx. And notice we're going to be able to plug that in a second. So I'm going to factor out that 3. Again, you don't have to do that, but I think it makes it easier to see what I'm doing. And you could even pull it all the way outside the integral if you wanted it. And then I'm going to make my substitutions. Okay, so notice this on top is 1/15 du, negative 1/15 du, over u to the fourth. And I could have written that du over here, it doesn't matter. Okay, now again I have a power rule integral. I'm going to rewrite it so it looks more like a power rule integral. So u to the negative fourth du, and then negative 1/15. And now it's so easy, right? That's like the power of this method. We have no way to solve this integral, but by being clever and changing variables, it becomes a really easy integral. So we get u to the negative third, and then we want to multiply by its reciprocal here. So we get 1/3, and then we already have a negative 1/15, so 1/45, u to the negative third plus c. And then I want to give my solution in the same variable I started with, so I'm going to replace my u. I'm going to replace my u with my original substitution. So I'm going to say 1/45. That's fine to leave that negative exponent there. That is, it's an x to the third actually. So there's my solution. Okay. So hopefully you're beginning to develop an understanding of the steps. So find u and du. So this derivative of the u that you pick needs to show up in the function as well. Otherwise you can't make this substitution because there's no way to substitute out this dx. Okay, so you have to change both your function and this derivative operator into u's, right? And sometimes it doesn't work. Sometimes you pick a u and you pick the wrong u, and then you can't get this derivative substitution to work no matter what you multiply by. And that's your cue that you need to go back and reevaluate your u, right? Again, pay attention to how I did this substitution. So from this step to this step is the important, challenging step. Okay? When you follow that, the rest of it flows from what you already know, right? So check your understanding of these two steps, and then I'm going to show you one more. So here, I just want to show you that this works for different types of functions beyond polynomial functions. So notice I have x to the third inside the cosine, and conveniently I have a derivative of an x to the third type function outside. That's my cue that I should use a u substitution, so I'm going to let u equal x to the third du equals 3x squared dx. Okay, and then I'm going to say 1/3 du equals x squared dx. Now I can substitute, right? So x squared dx is 1/3 du. Cosine of x to the third, well, that's cosine of u. Okay? And then this is just a antiderivative of cosine is sine, so 1/3 sine u plus c. And, of course, u is x to the third. So notice, like, if we did the derivative of this, we would use chain rule. Chain rule would give us this x squared on the outside, right? So that's where this comes from, is it's a way of sort of undoing the chain rule in a lot of cases. But that's my result. And again, here's this works for any type of function, not just polynomial functions. Here's an example of what it might look like. In your practice, you're going to run into mostly polynomial functions.